All right, so we're trying to prove this theorem, right? So Z was the span of V, T of V, up to T to the J minus 1 of V, right? Where J was the largest such that the set containing V up to T to the J minus 1 of V is linearly independent. Correct? So that's what we've done so far, and we proved about Z that it has beta, what we call this was beta. That beta is a basis for Z, that T to the J is an element of Z still, right? And that Z is T invariant. All right, so that's where we got. So now, my goal is to show that Z and W are one and the same, double inclusion. Z is T invariant that contains the element V, correct? It is a T invariant subspace that contains V. Didn't we say that any T invariant subspace that contains V must contain the T cyclic subspace generated by V? We said that that is the smallest, right? So V is in Z, and just to convince you, it was here, this idea. W is the smallest T invariant subspace of V, right? And Z is T invariant. This implies that Z must contain the entire T cyclic subspace generated by V, which we call W. All right, but what is W in fact? Well, W is the span of V, T of V, T squared of V, and so on, right? Dot, dot, dot. That's what the definition of W is. What was Z? The span of everything up to J minus 1. So it's natural that Z is actually part of W, right? Because it contains some of the vectors of W, right? Just by looking at the definition without doing any other work. In conclusion, Z is one and the same as W. And since the dimension of W was denoted by K, and the dimension of Z is what? J, right? J and K must be equal. So, V, T of V, up to T to the K minus 1 of V forms a basis for W. And we're done with part A. That's exactly what we needed. Part B. The connection between the linear combination that gives you T to the K and the characteristic polynomial of T sub W. Okay, so we said that because T to the K is in the span of all the powers up to K minus 1, it has to be a linear combination. So let's just say that this is that linear combination. Okay. So I want to show something about the characteristic polynomial of T sub W. That is again the determinant of the matrix of T sub W in some basis minus T identity. What basis? Well, I'll take the basis from part A, definitely. Basis what we call beta above. All right, so let's see what this matrix looks like. T sub W of the first element of the basis, which is V. Well, that is actually T of V, because T is just the restriction to W. So the first column is given by the expression of T of V in that basis beta. So what is the first column? This T of V is actually the second vector in the basis beta. 0, 1, 0, and zeros all the way. Right? The second column is given by T of the second vector, and that second vector is T of V. T of T of V is T squared of V, right? So expressed in that basis will be 0, 0, 1, and then zeros. Now keep going with this, right? The third one will be 0, 0, 0, 1, and so on, right? Until when? Well, until T of not of the last one, because that will give me T to the, by the way, I'm circling in the wrong place, J equals K, so maybe we should look here instead. This is beta, in fact, because we proved that J and K are equal. So I'm looking here now. So T of T to the power K minus 2 will be T to the power K minus 1, which is the very last vector in the basis. And that will give you 0, 0, 0, all the way down to 1. So now, what is T of the last element of the basis? Well, T of the last element, which is this one, right, is T to the K of V, correct? T to the K of V. But T to the K of V, actually I shouldn't write this down. T to the K of V is here, right? I know how to express T to the K of V in terms of everything else. Will be negative A0V minus A1T of V minus so on, right? If you move everything to the other side. So what will the last column look like of this matrix? Negative A0, negative A1, negative A2, negative A sub K minus 1. Okay, so that's the matrix. What do I have to show? I have to show something about the characteristic polynomial of TW, so I need to look at the determinant of this matrix minus T identity, identity K by K. So the determinant of the following matrix, negative T, 1, 0, 0, 0, 0, negative T, 1, 0. Zero, zero, zero. Well, 1, but keep in mind that above this 1 there is a negative T, right? Because that's where the diagonal is. Exactly one place above each one. And in the last column I have negative A0, negative A1, negative A2, and then finally negative A sub K minus 1 minus a T. Okay. What do I want to get? I want to get something like this. This is what I want to get out of it. So at this point, your trickiness about determinants will have to come into play. So I need a negative 1 to the k, first of all. To come up with negative 1 to the k out of this matrix, you can pull out a negative 1 from each column, right? Because once you pull a scalar out of a column, it goes out as that number. But to have it to the kth power, you have to pull it out k times. So I'll pull it out from each column, not with this color. All right, so now I want to do some kind of expansion of the determinant, but we've seen row expansions, right, before. I don't want to do a row expansion. What I want to do is a column expansion. Can I do this, first of all? Can I expand the determinant along a column instead of a row? Why not? Because the determinant of A and A transpose are one and the same. So if I want to do that, I can just take the transpose of the whole matrix, the column becomes a row, right? So I can very well expand the determinant along a column instead of a row. And I'll expand it along the very last column. The reason being that this is the expression that I want to get, the highlighted one, right? So all the terms contain some kind of A sub something, so. Okay, expand along column K. Yeah, I'm wondering if it was necessary to pull out the -1 to the K, but probably not, but we'll see. So what happens? I get A0, right, the first entry there, times -1 to the power 1 plus K, times the determinant of which matrix? Well, if you delete row 1 and column K, you end up with that matrix that is inside the highlighted region. What is the determinant of that matrix? Correct. So it's just the product of the diagonal entries, and there are k minus 1 of them. But we said there was a -1 to the k plus 1 because that's the position of a sub 0, right? That's how you expand along a row or a column. And then times the determinant of that matrix, which is -1 to the power k minus 1. K minus 1 times k plus 1 is 2k, which is nice, right? And that disappears. This is just 1. And that's pretty good, right? Here it is, A0 by itself, the first entry. We have that, A0 by itself, plus A1 times -1 to the power 2 plus k, or k plus 2, times the determinant of, I'll keep messing this picture up, of this one. Everything except the green stuff. It's still k minus 1 by k minus 1. What determinant does it have? There is a t and the -1 to the power k minus 2. K minus 2 times plus k plus 2 gives you again 2k. Those two things combined give you 1, and then you're left with A1 times t, right? A1 times t is exactly what we needed here, right? And it keeps on going until the very end. Okay. So in the end, the characteristic polynomial of the restriction will be exactly what they want it to be. Okay, so let's look at an example before we move on. T from R4 to R4. T takes a 4-type tuple A, B, C, D into the following: A plus B, B minus C, A plus C, A plus D. And W is the T-cyclic subspace of R4 generated by the following vector, the vector E1, 1, 0, 0. What's the question? The question is probably find the dimension of W and the characteristic polynomial of the restriction of T to W. All right, so what dimension could W have? Well, it's part of R4, right? It contains this vector E1. It must have dimension at least 1, but most 4, right? So it's a number between 1 and 4. And when you look at W, which is the span of E1, T of E1, T of E1, and theoretically it keeps on going, right? But we know that the basis is found how? We take that maximal linearly independent set, right? Depends on how far we can get. So let's compute them. E1 is E1. What is T of E1? What do we get? It's this one, right? A is 1 and everything else is 0. So 1, 0, 1, 1. Okay. Does E1 together with this vector form a linearly independent set? Because that's how the proof was going, right? Can we add this to E1? The answer is yes, right? They are independent. Okay, so then I keep on going. Maybe I can add the next one. What is the next one? Is T squared of E1 or T of this new vector? T of 1, 0, 1, 1. What is T of 1, 0, 1, 1? 1, negative 1, 2, 2, correct? Okay, so now if I put this one here, does this set containing 3 vectors now, is it still linearly independent? Without checking anything, I know it is because of this entry, negative 1, right? Because that's the only time when you have a non-zero entry in the second position. There is no way to generate that. So this is still independent, so that means I can keep on going, but how many times? At most once, right? Because I cannot exceed 4 with the dimension of W. So look at T cubed, which is T of 1, negative 1, 2, 2. A plus B, B minus C. Zero, negative 3, 3, 3. So now the question is, if I add this new vector to my set, is the resulting set linearly independent or not? Most probably not, but there is no way to find out unless you dig into it, right? So you have to actually check. So I set it equal. X plus y plus z is 1. So I'm done with x. Negative z is negative 3, right? From the second entry. From the third entry, y plus 2z is 3. Because z was 1, y has to be 1. And from the third entry, Same thing, y plus 2z equals 3. Isn't negative z equal to 3? Second entry of the resulting vector. Don't you get it from this? Negative 1 times z equals negative 3. So z is 1. Okay, so z is 1, y is 1, and x is negative 1, so it works, right? There are non-zero solutions, therefore this set is not linearly independent. So that means in that process for finding the basis, I should have stopped at 3. So I'm going to close the bracket here, and it turns out that this is in fact the basis for W. So the dimension of W is 3. That was the first question. But how do I answer the second question? What's the second question? Find the characteristic polynomial of the restriction. Yeah. Oh yeah, but still. But that's a good point because it will change the values. X plus y plus z is 0, so x is not negative 1, is negative 2. But still non-zero solution. But it matters. Why does it matter? Because it's going to matter for finding the characteristic polynomial. You go back to this, right? The characteristic polynomial, you can find it if you know how the next one, which makes it dependent, which for us was the fourth power, right? The fourth power made that thing dependent. If I know how to express that linear combination with the fourth power, and I should be able to based on the values of x, y, and z, I'm going to get the characteristic polynomial of the restriction. So I'll take the fourth power. Which is actually the third, right? It is the fourth vector, but it is the third power. So, which is that vector 0, negative 3, 3, 3. It is x, so negative 2 times the first vector, plus 1 times the second vector, which is t of e1, right? And plus 1 times the third vector, which is t squared of e1. So basically, negative 2 e1 plus 1 times t of e1. Well, this one had to be positive, so I'll flip everything around. Minus t squared of e2 plus t cubed of, not of e2, of e1, there is no e2. Plus t cubed of e1 equals 0. Right, I moved everything to one side such that t cubed has a coefficient of 1, because that's what the theorem requested. Okay, so then, can you tell me what the characteristic polynomial of the restriction of t to w is? This was like a0 of v plus a1 t of v, right? And so on. That was in the theorem there. F of t is negative 1 to the k times a0, so 2, plus a1t, so minus t, plus a2t squared, so minus t squared, plus t to the k, so plus t cubed. So pretty much you translate that linear combination into a polynomial of t. k is 3, sorry. Is negative 1 to the k, and we concluded that t was 3. Right? There were 3 vectors, right? So k was 3. So that's why I was saying that, you know, the mess I made here is actually important, right? The scalars that you get there out of the system define the right or wrong characteristic polynomial. Okay. The last thing, the Cayley-Hamilton theorem. So this one says that if f of t is the characteristic polynomial of a linear transformation t, then t satisfies it. In other words, if instead of little t in the polynomial you put big T, so for example, what does this mean? If, let's say, the characteristic polynomial of linear transformation is this, then by f of big T, we mean this. T squared, which is T composed with T, minus 2T plus 5 identity. And this being equal to T0 means that when you apply it to any vector v, you get 0. So that's what it means that t satisfies its characteristic equation. So if f of t is the characteristic polynomial, and it looks like that, then that's what f of t is, and it should always be 0. Okay, so that is unrelated to the theorem. It's just an example to see what's going on. So proof. So we need to show that f of t of every v is 0 for every vector v. Now clearly, if the vector is the 0 vector, we are done, right? Linear transformation, any linear transformation of the 0 vector is 0. If v is not the 0 vector, I can form the t-cyclic subspace generated by v. Okay? So that is the span of v, t of v, t squared of v, and so on. But everything happens in a finite dimensional vector space, right? So W must have a finite dimension, let's say K. All right? But that means that to find the basis for W, I can only go up to the K minus 1 power. That will become a basis for W, and again, I know what the characteristic polynomial of T sub W will be based on the way in which T to the K becomes a linear combination of those vectors. let's call that g of t. So negative 1 to the k, a0 plus a1t plus a k minus 1 t to the k minus 1 plus t to the k. Right, that's according to the previous theorem. Right, that's the characteristic polynomial of TW. What happens if I plug in the transformation into G? A0 identity plus A1t plus t to the k, right? And if I apply it to some vector v, I get A0v plus A1t of v plus a k minus 1 t to the k minus 1 of v plus t to the k of v. So what is this? Well, everything was constructed based on the assumption that this linear combination is 0, and that's exactly what we have here, right? We got the same thing as above, that is 0. So the characteristic polynomial of the restriction applied to the transformation t and to any vector v will give you 0. Okay? But that's not what we wanted. We wanted this to be true about the characteristic polynomial of t itself, right? Not the restriction. And the very first result that we proved today was that g of t actually divides the characteristic polynomial of t. Characteristic polynomial of the restriction divides the characteristic polynomial of t. And you know how it is. If something divides a bigger polynomial and the smaller one has the value 0 at any such point, then the bigger one, which is a multiple of it, will also have the value 0. And the remaining time, I just want to show you how to apply it. This is 18 on page 323. It says that A is a matrix n by n. The characteristic polynomial given by the following. First part, show that A is invertible if and only if A0 is not 0, and that's not something new. We've seen this idea before in the sense that there is a way to actually compute the free coefficient of the characteristic polynomial based on A. You know how to find it? You don't know the characteristic polynomial, but you want to find A0 based on A. What was the characteristic polynomial? It was defined to be the determinant of A minus T identity, right? A sub 0 is actually the value of f at 0. Plug in 0 for t, you get A sub 0. And f of 0, if you look towards the left here, is the determinant of A. So clearly A is invertible if and only if the determinant is non-zero. So if and only if A0 is non-zero. So this first part is not related to Cayley-Hamilton. If A is invertible, then you can compute its inverse based on this formula. Why? Because the linear transformation in particular matrix satisfies its characteristic polynomial. So according to Cayley-Hamilton, -1 to the n, a to the n, plus an minus 1, a to the n minus 1, plus a1a plus a0 identity is the zero matrix. Okay. So, negative. So based on this, now I know that A is invertible, right? How do I get A inverse? You multiply the entire thing left and right by A inverse. I mean the left side and the right side you multiply by A inverse. You get -1 to the n, a to the n minus 1, plus an minus y1, a to the power n minus 2, plus a1 identity plus a0 a inverse equals still the zero matrix. And you solve for this, move it to the other side, it gives you the -1 over a0, right, that you have in the formula above. And the idea is that this is something that can actually be used in numerical examples. So use part B to find a to the -1 for the matrix A equals 1, 2, 1, 0, 2, 3, 0, 0, -1. So what does part B say? I can find the inverse. I know it's invertible. The determinant is -2, right? The product of the diagonal entry, so it's invertible. But to find the inverse, it's enough to know what the characteristic polynomial of A is. So ft as we're out of time, I'll just tell you what it is. This is it. This is the characteristic polynomial of A. So what is A inverse? -1 over A0. What's A0? -2, right? Times -1 to the third, n is 3, right? Because it's a 3 by 3 matrix. I'm reading it from here. -1 to the third, so minus. A to which power? N is 3. A to the second power. Plus A sub n minus 1. So A sub 2, that's the coefficient of p squared in the characteristic polynomial, and that is 2. So this is A2, A3, A1 and A0. A1 is 1, A2 is 2, and A0 is 2, -2. So 2A to the first power, right? And plus A1, which is 1, identity 3 by 3. So to find the inverse, all you have to do is to compute a second power and add up 3 matrices in the end, which is not a big deal, right? For a 3 by 3 matrix in general, it's not that easy to find the inverse, right? For a 4 by 4, you would have to compute up to the third power, so it would be a bit more work, but still doable. All right, so this is the end of 5.4. So I'll stop here. This is the last section that the exam will cover. Take a look at the sample problems, and yeah. So again, the homework. Now, I was saying I was going to post solutions anyways, but for the ones that don't turn in the homework early, the solutions will be posted. So I don't know how that would work, but yeah. Yeah, so I'll figure out a way. Yes. Done?
Thank you.
Mm-hmm.